Okay, today's colloquium is dedicated to Professor Yuval Neeman, and first I would like to invite the President of Tel Aviv University, Professor Itamar Rabinovich, to say a few words.
שלום אחרי צהריים טובים, דבורה, עמיתים, תלמידים. I'd like to apologize to Professor Susskind for speaking in Hebrew, but it feels more natural to speak about Yuval in this university in Hebrew, and I'm sure the gist will be transmitted to you, Professor Susskind. אנחנו עומדים כאן כבר ביום שנה מאז פטירתו של יובל. הרבה ממה שנאמר בעת שיצא מסע הלוויה מאוניברסיטת תל אביב וליד הקבר ובהזדמנויות אחרות באותה תקופה נשאר נכון, כי נאמרו אז דברים עשירים, רבי תוכן שיצאו מן הלב והם היו נכונים. אני עצמי דיברתי על יובל כאיש הרנסנס, מדען, איש פוליטי, איש תרבות, אוהב היסטוריה, אדם שעיצב במידה רבה את דמותה של האוניברסיטה הזאת וקבע לה סטנדרדים לצד המפעל הספציפי של בניית בית הספר לפיזיקה. איש יחד עם קבוצת חבריו להקמת האוניברסיטה קבעו משלב מוקדם את היעדים וקנה המידה הערכיים והגבוהים של האוניברסיטה. אי אפשר להבין את המקום שהאוניברסיטה הגיעה אליו תוך פחות מ-50 שנה בלי להבין את תרומתו של יובל להקמת האוניברסיטה ולפיתוחה. ואותן תכונות שהפכו אותו למנהיג אקדמי דגול באו לידי ביטוי כמעט בכל תחום שהוא נגע בו, אם בתחום הצבא ב1 ליוני, כי יובל ראוי לביוגרפיה מקפת יותר ומצע יותר, שתעשה צדק ותיתן ביטוי
He was formulating, he gave the Hamiltonian formulation of lattice QCD, and later he developed Technicolor, and after Technicolor initiated people to move to work on supersymmetry. He's behind the matrix model definition of M-theory, the formulation of the holographic principle, where a theory of quantum gravity can be described by a lower dimensional hologram as a field theory, the complementarity principle, and nowadays the concept of the landscape. He is a recipient of the Sakurai Prize, as well he is a member of the National Academy of Sciences and the American Academy of Arts and Sciences. And as you know, when we hire a new faculty, one of the things we look for is we check is the impact factor. So nowadays it's very easy. We go to Spires and we check the data, the citation index. So I did the same for Lenny. So what I found is that he has more than 20,000 citations, and it has 7 papers which are renowned papers with more than 500 citations. So I believe with this data we can get you a job here. Okay, without any more words, let me invite Lenny.
Can you hear me? Yes. I see many, many friends here. What I'm not my Hebrew is not good enough to really quite follow what the President said. I did follow what Yaron said. I didn't hear it mentioned that I am an Israeli professor, or at least an Israeli physicist. This is an emotional occasion for me. I spent part of my formative years as a professor at this university, Tel Aviv University, and to some extent it is a great joy for me to come back to see not only to see old friends, but to be standing in a capacity, namely as a teacher in a university in which I was a teacher for 7 years. I did not leave Israel for any other reason other than my older daughters began to say we can't go back and forth anymore, it's ruining our social life. But it is a joy to be back. It is also a sadness to be back. The one thing that's missing is my old friend Yuval, and Yuval was an old friend of mine. We spent many hours together speaking in his office about physics, philosophy, sometimes even politics, which we didn't always agree about. We never agreed completely about anything, but we always had fun and excitement and enthusiasm in talking. Incidentally, I understand there are some of my old friends. I understand Matilda is in the audience here. Matilda? Oh my goodness! Oh, you look exactly the same. You haven't changed a bit. And Dvora is also here. Is that right? Huh? Right. Right. So for me, this is a homecoming, and thank you for having me, and thank you very much for inviting me to be the first Yuval memorial lecturer. Incidentally, I was here 1 year ago exactly when Yuval passed away, and as I said, it was a great sadness for me. In any case, what I want to tell you about is a conversation that I had with Yuval I believe it was 1971. It was when I first came to Tel Aviv University. I came as a full professor. I was a friend of Yuval's. And from time to time, he would call me into his office to talk about one thing or another, usually physics. He wanted to sound some ideas off me. And one of the ideas that he wanted to sound bounce off my brain, or whatever, was an idea that he had some years before. And let me say that it originated in a question which turned out to be an extremely profound question, one that I will try to take you through a little bit, but it was basically the question of whether physics is reversible or not. Now, let me just tell you very quickly what reversible means. Physics is reversible if a movie of a process, if you run it backwards, is also a possible process, then one says that physics is reversible. The Earth going around the sun, if you run it backward, it just goes around in the other direction, and you cannot tell by looking at the film whether it's a forward film of the Earth going this way or whether it's a backward film of the Earth going that way. This extends down completely to the smallest objects in classical physics, molecules and so forth. Although it may seem to you that many processes run backward are impossible, at the basic level of the laws of physics, the laws of Newtonian mechanics, for example, anything that can happen in reverse. That's a basic principle of classical physics. It is also a basic principle of quantum mechanics. The possibility, not the possibility, but the fact that anything that goes forward can also go backward. That's what Yuval was thinking about when he asked me about black holes and white holes. Well, I'm not exactly sure he asked me. Maybe he told me, but it seemed to me at the time it was partly question, partly assertion. His statement was, if I can figure, let's see, here it is. His statement was that physics, as we know it, is reversible. All the basic principles of physics are reversible, and therefore, if there are such things as black holes, there also must be such things as white holes. What are black holes? Black holes are what happens when things fall in and gravity pulls them together so hard that a hole in space forms that nothing can escape from. But if physics is reversible, that same process must be able to go in the opposite direction. And so there should be processes in nature where objects like black holes just spew out enormous amounts of things. Yuval, in fact, had an idea. The idea did not turn out to be correct, but that's not the point. The idea was that perhaps quasars were white holes. That did not turn out to be correct, but the question was a profound one. Let me tell you a little more about what it means to be reversible, about in particular in the context of black holes. This, of course, is a star. Imagine it's a large star. This happens to be our sun. Our sun is not really big enough for what I'm going to describe. Imagine a star 100 times more massive than the sun, or 1,000 times more massive than the sun. What will happen to that star in time is it will collapse into a black hole. All of the particles that make up that star will eventually collapse under the influence of their own gravity. Incidentally, for those who are not familiar with such diagrams, this is simply a picture. Time runs up, space runs horizontal, and this is a process in which a whole bunch of particles simply come together under their own gravity and form a new kind of object, which is a black hole. The edge of this diagram is the horizon of the black hole, and according to the principles of relativity, nothing can escape from such a black hole, because in order to do so, things would have to exceed the speed of light. This is the basic picture that physicists draw when they think about the collapse of a star or other object into a black hole. This is the basic picture. Yuval said, look, if this is possible, then it ought to be possible to consider exactly the opposite process. All you have to do is turn the diagram upside down. Remember, time runs up. If everything that can happen in reverse, then there must also be the possibility that a black hole will become a fountain of energy and spew out all the energy that was in the black hole in the form of the reverse of a collapse process. A sudden fountain of energy of enormous magnitude. In particular, the larger the mass of the black hole, the more the energy that would come out of this white hole. He called it a white hole. I don't know whether he invented the term white hole or not. And he said the basic laws of physics, the reversibility of the basic laws of physics, must ensure that this is a possible process. He advocated that astronomers go out and look for such things in nature. My reaction to it at the time, I do remember very clearly sitting on a couch in his office. Matilda was in the front office, and Yuval and I, this is when he was chairman of the department, I think it was around 1971, sometime in the middle of 1971. I said, Yuval, this doesn't sound right to me. There's something wrong with this. Yes, it's true that a star or an enormous amount of energy can collapse and form a black hole, but there are other things that can form black holes besides stars. And I remember it was the first time in my life that I used the example of a herd of wild elephants coming together and forming a black hole. This is a possible process, I told him. There's nothing in nature that would prevent a sufficiently large number of elephants coming together, contracting, and under their own gravity, eventually forming a black hole. Here's the black hole. I said, if this is possible, and you are right, then there must also be a possible process in nature where a black hole will simply evaporate into an outgoing herd of elephants. And surely you don't believe that. He thought for a while, and unfortunately, I don't remember what he said. This theme of physics and black holes being or not being reversible has occupied the attention of physicists for close to 30 years, maybe more, and it is finally more or less becoming clear whether or not, to what extent, the basic principles of quantum mechanics, in particular the reversibility of processes, is or is not destroyed by black holes. So let me begin by telling you a bit about black holes. Now, you all, of course, including Matilda, certainly understand this formula here. This is the metric, the Schwarzschild metric of a black hole, but I promise you this is the last equation on this, in this talk. Actually, it may not be the last equation. There may be one or two others. I'm going to describe to you what a black hole is by an analogy which I like. It's an analogy that I learned from Bill Unruh, and it's called the dumb hole. Not dumb because it's stupid, but dumb because it's silent. Here's the picture of a black hole that I like to think about when I'm trying to explain it to an outside audience. Imagine an infinite flat lake, a lake that's so big and so broad that for all practical purposes it's infinite. In this lake, a species of, well, we could think of them as fish if we like. I tended to think of them as pollywogs. A pollywog is a baby frog, but it hardly matters. They could be fish. Let's make them fish. But right at the center of the lake, well, an infinite lake doesn't really have a center, but let's define some place that's called the center. There is a drain hole, an opening that unloads the water, or that allows the water to drain through a hole and fall down onto some sharp rocks underneath. The water, the pull of the rocks below is so powerful that it eventually, at some point, causes the water to exceed the speed of sound. Now, there is a rule in this world of fish, that neither fish nor anything else is allowed to exceed the speed of sound. They have a fish law which says you may not exceed the speed of sound. They can't do it anyway. Their tails don't wiggle fast enough. Sound doesn't exceed the speed of sound. And so there's no way for them to communicate with each other in the time scale less than it takes sound to go from one to another. Of course, in the real world, we would be talking about light. As this water flows toward the drain hole, imagine that at some distance out, represented by this lighter line over here, the speed of the water toward the center becomes equal to the speed of sound. Now, far away, the water moves very slowly toward the center. As you move in, it picks up speed. At some point, it exceeds the speed of sound. And this is a very, very dangerous drain hole. Why is it such a dangerous drain hole? The main reason it's so dangerous is because as a fish or a pollywog or whatever it is crosses this point of no return, it's a point of no return, nothing can outswim the current because the current at this point is at the speed of sound. Nothing can outswim it. No message can be sent from inside this region here because sound will not exceed the speed of sound, obviously. But for a fish that's comfortably flowing with the flow, imagine a fish that doesn't know anything at all, is just flowing with the flow. There's nothing special going on here. Nothing special except that it's a point of no return. What makes it so darn dangerous is that there are no signposts, there are no structures there that tell a fish you have passed the point of no return. But once he's past the point of no return, that fish is doomed, has no choice but to fall onto the rocks below. This is the structure of a black hole. This is the way a black hole behaves. At the center is not rocks, is a singularity, and a far more dangerous place than rocks, of course. But outside and out beyond the singularity, there is a point of no return, and the point of no return is called the horizon. So for our purposes, without equations, this is basically what a black hole is. The main thing I want you to keep track of and to note is that nothing special happens to a fish as it crosses the horizon, flowing with the flow. Everything around it, all the debris, any friends that he might have, little bits of stuff flowing along with him, will flow together, and they will have no idea that he's passing the point of no return. But, nevertheless, that's the most dangerous place that that fish can be in. Now, in 1972, I believe, in 1972, Jacob Bekenstein asked a question about black holes, which also turned out to be very deep, very closely connected in many ways to Yuval's question. He asked about entropy. What is entropy? Well, we'll come to what entropy is, but you all know that there's the second law of thermodynamics, and the second law of thermodynamics says that entropy never decreases. Well, Jacob Bekenstein asked a very simple question about a black hole. He said, supposing these fish take a box of gas, some sort of container containing hot gas full of entropy, and throw it into the black hole. If it's thrown into the black hole and it goes through the horizon, it's gone. It cannot send signals out. For all practical purposes, that box of gas has disappeared from our universe. The consequence of that would be disastrous for the second law of thermodynamics. It would say that entropy can easily be made to disappear just by throwing it into black holes. His answer was, the second law of thermodynamics is far too deep to be thrown away that easily. And so, my conclusion must be that when you throw things into black holes, the black hole itself has an entropy. The black hole has an entropy which is in some way or another proportional to the size of the black hole. When you throw things into the black hole will expand, and in some way or another the expansion of that black hole will indicate that the entropy of the black hole has increased. Black holes must have entropy related to their radius. In fact, Bekenstein made some estimates based on some neat little theory to estimate that the entropy of a black hole was proportional to the square of the radius. In other words, to the area of the black hole. If black holes have entropy, and if they also have energy and entropy go together, and they define temperature together. In fact, the temperature is nothing but the change in energy if you increase the amount of entropy by 1 unit. So, since Bekenstein said when you throw a unit of entropy into a black hole, it must get a little bigger, therefore a little bit heavier, it implied the existence of a temperature. That was first realized by Stephen Hawking. Bekenstein realized that black holes have entropy. He had a formula. His formula did not actually have a 4 here. It had an unknown constant. It was Stephen Hawking who provided the constant, but it was also Stephen Hawking who realized that the combination of energy and entropy of a black hole meant that it had a temperature. Here is the formula. I promised you no more formulas, but you needn't remember this. This is the formula for the temperature of a black hole. The interesting thing about it is that the temperature decreases as the mass gets larger. But because it has a temperature, black holes radiate. They radiate black body radiation, and they eventually evaporate. That was the early 70s, or mid-70s, or early 70s. As a matter of fact, much of this must have taken place at just about the time that I was talking to Yuval in his office, but neither of us knew anything about it. What does it mean for a system to have entropy? Entropy in physics is hidden information. Information that in principle you could get, but which is hidden for one reason or another. One way of hiding entropy, one way of hiding information is just to have it be contained among degrees of freedom which are so small and so microscopic that you can't keep track of them. For example, a bathtub full of hot water, here's a bathtub full of hot water, doesn't look like it has anything interesting going on, it's flat, it's all the same temperature, but if you looked at it through a microscope, you would discover that it's full of molecules. The position and energy and momentum and direction of every molecule is a degree of freedom, is information which is there in that bathtub full of water, but which is too small for you to see. You cannot keep track of it because there are too many molecules, and you lump it all together and you say it's simply it's a bathtub full of hot water. Entropy is a measure of the amount of information which is unavailable to you because it's too small and too hard to see. In fact, to be precise, it's the logarithm of the number of quantum states that can't be distinguished by us big, coarse-grained creatures who see the bathtub. So that's what entropy is. It's missing information contained in microscopic degrees of freedom. What was the implication? The implication for black holes is that there must be some kind of hidden microscopic degrees of freedom that make up the entropy of a black hole. Since the entropy of the black hole is proportional to the area of the horizon, the implication is that somehow the horizon of a black hole is made up somehow of a lot of little things that not only can't we see because we can't see black holes, but even if we could get right up close to a black hole, all of this stuff would be much too small, plunky in size objects that would be much too small to see. And that was the implication, at least that was the implication that I would have drawn had I known about it at that time. It was not the implication that Stephen Hawking drew. Stephen Hawking drew a different implication. He drew the implication that there was some new kind of entropy which had nothing whatever to do with number of degrees of freedom, with number of quantum states of a system. Let me go a little bit ahead. Let me tell you a little more about black holes and their horizons. Do black holes have a hidden microscopic structure at the horizon? Well, let me tell you some of the properties that they do have. And about this, there is no ambiguity. For example, here's a property. The horizon of a black hole is very hot. I told you that the black hole was cool. That's if you look at it from a great distance. If you look at the black hole right up close, you will find it's very hot. If you were to take its temperature by lowering a thermometer down to someplace near the horizon, you would find out that the horizon got hotter and hotter and hotter as you got close to it. That sounds a little strange because remember, the fish flowing past there would feel nothing special, something a little bit strange going on. Another thing that the horizon has, it has electrical conductivity. If you were to take a circuit involving a battery and a voltmeter, put the leads across the horizon of the black hole, you would find that it has a conductivity, as if charges could flow through the horizon of the black hole. Another thing, if you drop something down onto a black hole, a lump forms on the horizon. That lump spreads out, and because it spreads out in a way that's consistent with saying that the black hole horizon has viscosity. Entropy, viscosity, temperature, electrical resistance. If you looked close to the horizon of the black hole, you would find that this high temperature leads to particles constantly being emitted and reabsorbed by the black hole. Some of those particles, if they were ejected straight upward with enough energy, would escape the black hole, and they would be the Hawking radiation. So it seems like, from at least as measured from the outside of the black hole, the horizon is full of properties that would be detected by anybody who got close to the black hole and sent the probe down. On the other hand, The equivalence principle, Einstein's equivalence principle, had a different story to tell. The story that it had to tell was that anything that falls into a black hole freely sees absolutely nothing unusual at the black hole horizon, no electrical conductivity, no high temperature, or anything else. It was a puzzle. It was a puzzle which was a conflict of principle. The conflict of principle was a conflict between the equivalence principle and the conservation of quantum information. To say it another way, conservation of quantum information is what Yuval called reversibility, that things that can happen forward can happen backward. Here's a little picture that illustrates a Gedanken experiment. Imagine observers, they could be these little fish, or they could just be ordinary observers, falling into a black hole. Falling into a black hole at a rate which is fast enough to compensate the tendency of the black hole to evaporate. So every so often, another observer jumps in, just at the rate which is necessary to keep the black hole from evaporating. That black hole will last forever and ever. Each observer or each fish brings in a little bit of information into the black hole. At the same time, Hawking radiation is going out. According to Hawking in 1976, this was something new, something totally new, that information brought in from the outside could get lost, destroyed at the singularity, and not be re-emitted among the products of the evaporation of the black hole. To put it another way, Hawking was saying that physics is fundamentally not reversible. It will not remember that what fell in here, these bits of information, what will come out will be absolutely featureless with no memory of the things that fell in, number one. And number two, even worse, you could throw in an infinite amount of information with none of it ever coming out. That was a contradiction. That was a fundamental contradiction with the principles of quantum mechanics, which would say that if you throw in more information than the area or the entropy of a black hole, it must start coming out and it must start leaking out. So Hawking's position was that black holes destroy the reversibility of physics. Stuff comes in, featureless stuff goes out, and you can never reverse it. Yuval's point of view, at least at the time, was that physics is reversible, and therefore white holes must exist if black holes exist. In other words, the process of radiation coming in, featureless radiation coming in, must allow the possibility of fish being emitted from the black hole. There were two stories. An irreversible story that said that as things, people, observers, and so forth, fall into a black hole, they fall behind the horizon, and once they fall behind the horizon, they can never get out, and they can never carry out the information with them that fell in. That was one story. It goes together with this diagram. Things fall into the black hole. They can never come back out, because to do so, they would have to exceed the speed of light, and so physics must be fundamentally irreversible. The other story was a story which was consistent with the principles of quantum mechanics, but grossly different from the previous story. And that said that as an observer fell toward the horizon, they would encounter these hidden degrees of freedom, this tremendous heat that's present at the surface of the horizon of the black hole. They would be heated, disassembled into their constituents, and radiated back out as black hole Hawking radiation. These seem to be two completely conflicting stories, that both of which had very good reason to be true. One of them is that the principles of quantum mechanics says that nothing could be lost. It had to be radiated back out, and at the horizon of the black hole there was tremendous heat. The other story saying that the horizon is nothing but a point of no return, and you can cross it freely. Nothing will happen to you until you get to the singularity. This was a fundamental puzzle of physics that, that has really only gradually been resolved, and I would say even some people still say is still unresolved. I think it's false, but we'll come to it. What is the truth? Which of the two stories is correct? Is it correct that something falling into a black hole will pass into the interior, never ever be able to get out, and every bit of information that goes in with it is fundamentally lost? Or is the correct story that as things fall into a black hole, they arrive at a very hot place near the horizon? Even before they get to the horizon, they get cooked, they get ionized, they get turned into radiation and emitted back out even before they reach the horizon. Which is the correct story? Well, I quote here Sherlock Holmes. You can read what Sherlock Holmes said above. When you have eliminated all that is impossible, whatever remains must be the truth, now, no matter how improbable. The answer seems to be that both stories are true, depending on who is telling them. Now, that's a very common situation, both stories being true depending on who is telling them. So there's nothing particularly unusual about that. But in this case, the two stories have to do with whether you're outside the black hole watching it or falling through with the material. Both stories are true, even though they sound completely contradictory. The principle that says that both stories are true is called black hole complementarity, and I'll tell you a little bit about it. This is not the first time in physics that things which seemed completely contradictory turned out to both be true in a certain sense. The concept of complementarity is the idea that in a certain sense two things can both be true. But what we have to do is to learn to use the word or instead of and. For example, light is waves and light is particles. No, light is never waves and particles. Light is either waves or particles depending on what experiment you do. For example, if you have a laser and you send a beam of a large number of photons, enough photons to form a light wave, those light waves will create an interference pattern, and that interference pattern will look very wave-like. Or you can do another kind of experiment. The other kind of experiment is you send through such a diffuse beam of light that one photon comes through at a time. You watch that beam of light, and what do you see? You see a spot over here, you see a spot over here, then you see a spot over here, and so forth. You never see both the wave properties of light and the particle properties of light at the same time. And I would say that the use of the word complementarity implies changing and to or. Either you do an experiment that sees the wave properties of light, or you do an experiment that sees the particle properties of light. Here's another example. According to classical physics, particles have position and momentum, position and velocity. According to quantum mechanics, according to the complementarity idea, position and momentum are complementary variables. A particle either has position, or you describe a particle either as having a position or as having a momentum, not both. Here is a picture of Heisenberg's microscope. Let me just remind you how Heisenberg's microscope works. You might say to yourself, if particles can have position, and if they have position at each instant of time, then you can follow their position, and if you follow their position, you'll be able to determine their velocity. So it's not really consistent to say that particles cannot have both position and velocity. Well, Heisenberg asked himself the question, could you measure both the position and velocity of a particle? And most of us who've studied a bit of quantum mechanics know the answer, that you can't. But basically, here was the setup. He said if you wanted to see the position of this particle at the center of the microscope over here, you'll have to hit it with some light. If you hit it with some light and you want to see it sharply, you have to hit it with short wavelength light. If you hit it with short wavelength light, and remember that short wavelength light is very energetic, then the process of looking for the particle and detecting where it is will give the particle a huge kick, and in the process just make impossible the measurement of the other variable. In other words, in trying to prove that this particle over here is both at this position and standing still, the process of measuring its position will destroy the possibility of measuring its momentum. That's what's called complementarity. Well, it seems that we're in a situation with black holes where two conflicting stories both seem to be true. What we now think is that these are two complementary stories, complementary in very much the same way as position and velocity are complementary, or wave particle aspects of light are complementary. How are they complementary? A given experimenter can only do one of two experiments, and not both. Can either stay outside the black hole and measure its properties, or fall into the black hole and measure its properties. Not both. For an observer outside the black hole, the horizon appears to be composed of a collection of hot, Planck-sized degrees of freedom, and all information that falls onto the horizon is absorbed, thermalized, or scrambled, and re-emitted with the Hawking radiation, according to the usual reversible laws of quantum mechanics. That's a picture from the point of view of the experimental physicist who stays outside the black hole. From the point of view of the freely falling observer who falls into the black hole, the horizon is simply empty space, nothing present. All information passes into the horizon without encountering anything out of the ordinary. Passing the horizon is a non-event. These two things appear to both be complementary and both correct descriptions of what happens, but no experimenter can do both, just as no experimenter can measure the position and velocity at the same time. And that is how it is possible for particles which have position to not have momentum, and vice versa. Well, let me carry it a little bit further and show you a little more about how complementarity works. Here's a picture of a particle falling into a black hole. If we watch that particle and we move with that particle, nothing special happens to that particle. It continues to look like a little tiny particle. And if we follow it into the black hole, we would calculate that it passes the horizon at a certain very definite point and then goes into the black hole where it might eventually hit the singularity. It leaves a little spot on the horizon. Well, it doesn't even leave a spot on the horizon, but the point where it crosses the horizon is practically a point, no bigger than the particle itself. That's the story as told by somebody who falls through with the particle. The particle itself feels nothing special out of the ordinary and behaves perfectly particle-like. On the other hand, the story from somebody who stays outside the black hole is that the black hole horizon is incredibly hot. Remember, as you get closer and closer to the black hole horizon, the temperature goes up and up and up. What happens to a particle that enters into a very, very hot environment? It starts getting kicked around by thermal, hot, fluctuating degrees of freedom. What will it do? It will get, well, if it's an atom, it will get ionized. If it's a nucleus, it will get smashed into quarks. If it's a quark, who knows what happens to it then? But it will eventually get spread by the process of thermal activation or thermal vibrations, thermal whatever. It'll get spread all over the horizon. Two entirely different stories. How can they both be true? One seen from the outside, one seen from close by. Well, here's what we might propose to do. We might propose to get ourselves a microscope and look extremely closely at where the particle falls through and see if we can falsify this crazy idea that the particle gets diffused, that it gets scattered, that it gets bumped, all random walks, that it basically random walks all over the horizon. This should not be so hard. What we should do is get ourselves a Heisenberg microscope. The Heisenberg microscope consists of an incoming beam of radiation, which happens to be aimed at just the point where the particle goes through the black hole horizon, backscatters out, and we look at it, form an image, and ask ourselves, does this particle form a point when it passes the horizon, or is it spread out all over the place? Now, you might think that this is an easy experiment. in order to be more and more precise about the position of the particle, we ought to use shorter and shorter wavelengths. If we use extremely short wavelengths to try to see exactly what happens when we get very close, extremely short wavelengths are very, very good for localizing a position, localizing exactly where the particle went through the horizon. And so it should be possible to disprove this claim that the particle gets scattered all over the place. But we have to take something into account. As time goes on and this particle gets closer and closer to the horizon, in order to see it, we will have to use higher and higher energy radiation. At some point, the photons that we will use will exceed the Planck mass, the Planck energy. In particular, as the particle gets within a Planck radius of the horizon, to see it clearly, you will have to use photons way above the Planck scale. So we can ask the question, what happens when particles collide? The particles which are colliding now are the radiation of Heisenberg's microscope with the particle falling in. What happens when particles collide at very high energy? Here's a picture of two particles colliding, and for arbitrariness, I've just said, let them have an energy 1,000,000 times the Planck mass. A very, very high energy, and it's not entirely clear to anybody that we could ever achieve such energy with accelerators and so forth. But let's for a moment imagine that we could scatter particles together with high enough energy that we could resolve distances 1,000,000 times smaller than the Planck scale. What will happen? Well, here's what will happen. When you collide those particles together, instead of being able to see what's going on right at the center, a black hole will form. Why? Because we've created so much energy inside a small region that a black hole will naturally form. The more energy we try to squeeze into that region, the more we try to see the details of small distances of what's going on very locally, the bigger the black hole will be. What will happen to that black hole? That black hole will evaporate, but it will evaporate with longer and longer radiation, longer and longer wavelength radiation. The result will be, in the attempt to try to see what was going on closer and closer at smaller and smaller distances, the result, when we get to too high in energy, will be to diffuse the description over a larger and larger radius. Well, you can more or less guess now, let's go back a step, you can more or less guess now that if you try to look too closely with better and better resolution at what happened to that particle as it passed through the horizon, you will not be able to tell that it didn't get scattered all over the horizon like this. This is another example of this kind of complementarity, where by trying to do a measurement to disprove that a particle goes through a horizon without getting scattered all over the place, you wind up causing exactly the phenomena that you were trying to disprove in the first place. This is called black hole complementarity, and it's one of the sort of basic ideas that's come up in the last few years. Let's not do that. Yes, maybe we should. The same idea has been applied in string theory. Incidentally, you don't have to believe that string theory is the right theory of nature to use it anyway. How do you use it? Let me tell you how you use it. String theory is a theory that contains gravity and quantum mechanics. You can test out ideas with it, even if you don't believe it's the right theory. You can test out ideas such as the idea that information is lost or physics is necessarily irreversible because of black holes. You can use string theory, which appears to be a consistent mathematical framework that contains both gravity and quantum mechanics. You can test out the idea. What you might find is that, in fact, when you work out the equations, string theory says that information is never lost, that, in fact, these ideas of black hole complementarity are correct. If so, that doesn't prove that string theory is the correct theory of nature. It just proves that Hawking was wrong about the inevitability of losing information, the inevitability that quantum mechanics plus gravity does that. Well, here's a picture of what a string theorist might expect about a particle falling toward the horizon. As it gets closer and closer to the horizon, it encounters a region of increasing heat. As seen from the outside, it will seem to spread itself over the whole horizon. That's what somebody from the outside would argue. And if somebody else tried to say, prove that this didn't happen, they would run into exactly the same situation that I described before, that by trying to use a Heisenberg microscope to see that this doesn't happen, they would cause it to happen. They would cause the string to get spread all over the horizon. So string theory has its own kind of black hole complementarity. A very crude cartoon of what string theory has found for the fundamental missing hidden degrees of freedom is that the black hole horizon is covered with little bits of string. Now that's a tremendous oversimplification. All of my string theorist friends will jump up and down and say, well, that's not exactly true. This is a crude cartoon of what string theorists think the horizon of a black hole looks like, that it is a surface, a two-dimensional surface, which contains all the information, all the material that ever fell into the black hole, and it's all contained within a wildly varying, fluctuating structure, one big string, basically. What is the hidden information? The hidden information is all the detail that's too small to see, because it all takes place at the Planck scale. String theory has, to some extent, confirmed that. Now, I'm not sure. How much time do I have to... 20 minutes. Okay, good. All right. That's the idea of black hole complementarity. I want to tell you, before we get back to Yuval's question, I want to tell you another idea which has emerged over the last 10 years, well, a little more than the last 10 years, which is another extremely bizarre idea. I want you to understand, this is very bizarre what I told you, that two seemingly totally different stories about where things are located, what happens to things, both seem to be possible, both seem to be true, depending on who looks at it. I'm going to tell you another bizarre story, which is very closely related. Originally, most people who studied the quantum theory of gravity had the idea that what you should do is divide up space into little Planckian cells, no bigger than about the Planck size. It was understood that the quantum field theory of gravity leads to divergences at small distances. They proposed to do exactly what lattice gauge theorists did at a somewhat later time, simply to divide space up into little cells which were indivisible so that you couldn't pack too much stuff into a cell, and in that way get rid of the divergences of the theory. That was the basic idea that held sway for many years, that space has a smallest distance and a smallest cell size. You could call those cells voxels. Voxel is the three-dimensional version of pixel. A pixel is a two-dimensional little element of area. A voxel is a three-dimensional little element of volume. And the idea went, each one of these voxels would have a small number of degrees of freedom, maybe just a binary degree of freedom, something in there or something not in there. A kind of grand tic-tac-toe lattice, plus, minus, or yes, no, or binary qubits, or whatever we would like to call them, and that the whole world was made up out of bits of information stored in space in this form. John Wheeler called it from bit, meaning to say that material, real things, were composed out of bits of information distributed throughout the volume of space. Now, here's an example. Here's a crystal lattice. This crystal lattice can have a red particle in it or not have a red particle in it. How many bits of information can you hide in these Planckian cells? By hide, I mean not be able to see necessarily because it's too much fine structure. It's quite clear that the amount of information is proportional to the volume. The number of bits of information, the number of qubits, the number of question is also called entropy. Entropy and hidden information are the same thing. Now the question is, and asking what the maximum number of bits of information that you can hide, you're equivalently asking what the maximum entropy of a region of space is. It had always been assumed that the maximum entropy of a region of space would be proportional to its volume. But because of Bekenstein's understanding of entropy and Hawking's work afterwards and so forth, both myself and 't Hooft came to a very, very different conclusion. And here was the conclusion. Here's how it works. Supposing you take this region with all of its stuff in it, and you surround it by some shell of mass, and you collapse the shell of mass. This is a shell of infalling mass which is coming in. Just enough mass to turn this region of space into a black hole. You can always do this. Everybody who does general relativity will agree that you can take this region of space, implode around it just the right amount of mass to turn it into a black hole of exactly the same size. What will be the entropy of that black hole? The entropy of that black hole will be its area. But that means the entropy of this original collection of gas in here, or whatever it is, must be less than its area. This is the area in Planck units, the area of the horizon. So all they can have entropy can this. Therefore, the original size of this region less than the area. What it says is that a region of space requires no more degrees of freedom to describe it on the surface boundary of the region. That led to what is called the holographic principle, that the maximum bits of information that is needed to describe a region of space is proportional to the area in Planck units. The world is described by pixels, not voxels. In other words, there is some mapping from the bulk of space to the boundaries of space, wherever you decide to put the boundaries of space. It doesn't matter much. It could be the walls of this room. It could be some sphere as big as whatever you like. You take some region of space and you ask, what is the right description, the right quantum mechanical description consistent with gravity and consistent with the principles of black holes? And the answer is that there's mapping, an unknown, complicated mathematical mapping that goes on in the area, and the voxels are the pixels on the boundaries of space. This is the world is a kind of hologram with all of the information stored on the surface far away. Well, there are very few string theorists who doubt this holographic description by now, and it has become one of the real mainstays of physics over the last 10 years. The world is a hologram. You can say that it is completely describable in some way by the things which are going on the walls of the room, and not any reference to the things that are going on in the interior. These are the things, are some of the things that that black holes, thinking about black holes, have taught us about the combination of gravity, quantum mechanics, information, locality, and the way things are stored in space. And it's not like we thought. Things are extremely different, radically different than we had originally thought. What things? The way that information is stored. Very much more novel than we thought. All right, I'm going to tell you now just a very brief things about how string theory, the real mathematics, the hardcore mathematics of string theory, has confirmed these two ideas, black hole complementarity and the holographic principle. I'm going to go through it very quickly. The study has been a study of quantum gravity in a space-time called anti-de Sitter space-time. Anti-de Sitter, not because it was invented by the antiparticle brother of de Sitter, neither because it was invented by the aunt of de Sitter, just because it has the opposite curvature as de Sitter space. This is what a spatial section, in other words, at an instant of time, this is, of course, Escher's famous drawing, limit circle number 4. It's called Angels and Devils. The point here is not the angels and devils, it's the geometry. This is what a slice, a spatial slice through anti-de Sitter space would look like. Each of these angels and devils could be thought of as a galaxy, and each galaxy is exactly the same size as every other, but because of the same reason that Greenland looks so big when you plot it on a plane, Greenland looks bigger than Africa because of the curvature of space, the curvature of the Earth. Because of the curvature of space, what is tiny out here is really the same size as what goes on here. This is a picture of the space of anti-de Sitter space. But anti-de Sitter space is a space-time, and it would actually look something like this. Vertically is time, horizontally is space. Space has this character of negatively curved, anti-de Sitter, Escher's famous drawing, and time just runs upward. There are two descriptions of what goes on in this anti-de Sitter space. One is the description as it would be given by the angels and devils if they were doing ordinary experiments inside this space, and they would say that all has a label, has a certain that there must be correct mathematical inside this is entirely contained in a field that lives on the label. In fact, a quantum field theory which lives on the label. This, of course, is the famous Neutrino conjecture. It's much more than a conjecture right now. It's not a theorem, not a theorem, but it's a thing that's been cross-checked in so many situations that we now all believe. Not everybody does believe. Completely describable by a theory which lives on the boundary, holographic theory, that the world in the interior of this anti-de Sitter space is a hologram of a quantum theory, and this would be a Feynman diagram living on the boundary of space. Furthermore, this theory has no more than 1 degree of freedom per area. A paper that was worked out by a Whitney myself, having those degrees of freedom, and consider the 1 degree of freedom per area. Exactly that principle. I want to tell you demonstrating that the things which I have to do are correct. This happens to be a picture of a black hole in anti-de Sitter space. There are black holes in anti-de Sitter space. They would look more or less like this, with this horizon of the black hole, the interior of the black hole, and all the things about black hole complementarity that I told you about can be checked with some degree of rigorous precision mathematics. They are correct in this particular situation. The bottom line is that there is no serious doubt among serious people, and serious people are people who agree with me, of course. There is no serious doubt that black holes respect the basic laws of quantum information theory. Say, information is never off, scrambled, it may be heated, it may be turned into scrambled eggs from, hard to decipher. The code for decoding it may be very, very difficult, but there was no longer any serious argument that the basic laws of reversibility are respected by black holes. But the cost seems to be that information is not localized in space in any way which is in any way similar than we had originally thought. That our ideas of space, time, and matter were badly deficient. We don't really know what's going to replace them, but we do know that there's going to be some very new concepts which are very different than the classical picture of space and time. What about Yuval's question? Can a black hole suddenly turn into a fountain of energy? Or a herd of elephants? Well, one answer is no. It violates the second law of thermodynamics. A fountain of energy, of coherent energy coming out of a black hole, or a herd of elephants, has much less entropy than the black hole that you started with. So the answer must be that the second law of thermodynamics forbids a black hole from suddenly turning into either a fountain of energy or a herd of black holes. On the other hand, the answer is also yes. Physics is reversible. Entropy, the second law of thermodynamics, is a different kind of law than Newton's law F equals ma. It is not really a law that says entropy increases. It's a law that says that entropy probably increases. Almost always entropy increases. But unlikely things do happen. Wait long enough, do it enough times. Poincare recurrences are certainly the extremely improbable things that will happen, but which will always happen inevitably if you wait long enough. For example, all the air in the room could suddenly rush into one corner. That would rather badly violate the second law of thermodynamics, but the second law of thermodynamics does not say it can't happen. It only says it's exceedingly unlikely. Events which reverse the increase of entropy are very unlikely. So unlikely, I did calculate, but I forgot the number, what the probability of a black hole turning into a herd of elephants is. It is, as you might expect, incredibly unlikely, but the reversibility of physics, as Yuval foresaw, implies that yes, it can happen. The second law of thermodynamics would say astronomers don't bother looking for it. Thank you very much. Yes. Yeah, that's a fair question. I think the answer is here's the experiment. You measure the mass of the black hole. You calculate where the horizon would be. You make the very, very precise calculation in terms of a very, very precise measurement of the mass of the black hole. And then knowing where the horizon is, you then focus a beam of very high energy photons down to that point and check exactly where the particle is. As you try to do that more and more accurately, you will wind up blasting the particle all over the horizon. All right? So knowing where the horizon is a theoretical calculation that you might do. Or you can actually, if you're on a space station surrounding a black hole, you can lower something in. You can lower a thermometer in, have the thermometer connected by cable, and lower it in, reel it down, 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 until it gets exceedingly hot, and you say that's where the horizon is. So you can measure where the horizon is from outside. You can't measure where the horizon is if you're a freely falling observer falling through. Yes, sure. Yeah. It fails. Here's the situation in which it fails. You calculate you pick a region of space. We're going to work in a region of space, and we're going to say, how dense do things have to get before it begins to fail? So you calculate the maximum entropy by calculating the area. And then you say, when the entropy in this room starts to get up to something like 1 per area out there, it's going to break down. Now, if you realize that's a lot of entropy. Why? Because the Planck area is so small. No, I mean, in a strict sense, I think yes. But I gave you the example of somebody feeding the black hole. You create a black hole, and then you sit there feeding it with energy at exactly the rate that you expect it to decay. And after a very, very, very long time, it comes to some equilibrium, and that equilibrium is described approximately by the eternal black hole. So it's not so different than a box of gas. I mean, the gas in this room did not exist here forever. But if you seal off the room, close it off, and you wait 15, 20 minutes, or 3 hours, or 100 years, it will be described by a completely time-independent stationary state. The equilibrium black hole, the eternal black hole, is the approximation to the equilibrium configuration of these degrees of freedom that make up the horizon of the black hole. But I think you're asking me whether, I'm not sure whether you're asking me whether the diagram that people draw when they talk about the Einstein. Certainly part of it. It's certainly part of it. Well, it is. It's definitely part of it. Not only, it's a small part. The fact that you measure particles. The great puzzle is what those particles do to you as you fall into the black hole. From one point, particle. The laws of quantum mechanics you would find. On the other hand, if you fall through with it, no such thing happens. So there seems to be a conflict. Really, the complementarity is that conflict, but it's driven by the observation that one observer sees hot particles near the horizon and the other doesn't. Does that answer your question?
Can you comment about the experimental verification of holography and
Absolutely. Absolutely. It's easy. You just go to Long Island, to Brookhaven, where they are now doing experiments, smashing together particles and forming black holes and seeing the black holes evaporate. Now, you can please explain that to the audience.
Other questions? If not, let's thank Lenny again.
How are you? How are you? It's nice to see you.
For my credit or to your credit that I could follow your lecture in a broad line.
I take that as an enormous compliment. Incidentally, the story, as I told it, about sitting in Yuval's room is absolutely correct. I mean, it happened exactly that way. Right.
Okay, nice to see you.
It's nice to see you.
I haven't seen you since the 70s.
That's right. But I'm going to renew. I have decided it's time that I renew my relationship with Israel somehow. I miss it badly.
Is somebody calling you on the phone?
No, this is the microphone that is recording our message for the rest of the room here.
Nice to see you.
Hello.
Is the reversal of the black hole?
Sorry?
Is the reversal of the black
Yes.
hole going through a wormhole, maybe?
Well, I think that picture is not part of what we think now. No.
I'm very happy to
How are you,
meet
Matilda?
Bye.
It's been a long time.
40 years.
Not quite. Almost. 40 you are.
When are you leaving?
So leaving.
Now, one of the most interesting folks I've had
I can't believe this. Israel must be good for people. They all look exactly the same.
Sure. I mean, I'm the
You
same.
look a little.
79, but it's okay. How old are you? 65? 60?
66. 67. 67. Almost 67.
What happened to your daughters?
Oh, let's sit down someplace.
I can't, unfortunately.
They're all fine.
Are you a grandfather?
Oh, yes.
How many
6 times
times?
older. 6 times. 6 times, but all from my daughter Lana.
Oh, just
Yeah. She looks like a little kid. She looks exactly the same. She really looks exactly the same as when she was. She's been through 4 husbands, all sorts of complexity in her life. And at the age of 40, she decided to go back to grad